Alright, welcome Jamie. So hopefully you're happy with your test score. So let's go ahead and let's go over it though, starting with our next section. So chapter 9, so page 129. Alright, so this was talking about chemical bonds and intermolecular forces. So how atoms stick together, first off, and then also how molecules, those larger units, how they stick together. You're going to talk about a chemical bond. A chemical bond is an attractive force between atoms that is strong enough to enable the group to act as a unit. Now, what do we call it whenever you have just two atoms put together? This is a term I believe we've already discussed, I think in chapter 1. Anyone remember? This is way back here though. Alright, Chris?
Is it compound?
A compound is two or more different atoms, specifically molecule. So a molecule and a compound is two or more different atoms specifically put together. So if you don't remember that term, to make a note for it, so a compound is composed of two or more elements that have been combined chemically together. Chemical bond is what holds them together. There are 3 basic types of chemical bonds. You might remember some of these from physical science, because I already taught it this year for physical science, and I always get a little bit confused because chemistry and physical science overlap, but they're slightly off, so I always get a little confused over what I've talked about in one class and not in the other one. So, you might remember them with the idea of covalent bonding, ionic bonding, and metallic bonding. These come back now. So, that's the idea we're studying these over again. So, if you go back and if you think, I loosely remember them, I didn't get it, it's okay. We'll go through them again this year. So, your book points out that you have a molecule or ionic crystal. So, if it's an ionic crystal, what's it made of, Quentin?
Crystal. Ion.
Ions. What's an ion? I don't think it tells you on this page.
We probably will.
We've talked about ions, I think, way back in chapter 2.
We was talking about ionization. Electrons?
What? Okay, so it's a different. So, are you gaining or losing electrons?
Losing. Gaining. Losing.
Technically, it's both. So, if you're gaining electrons, what type of ion are you? What type of ion are you if you're gaining electrons?
Positive. Negative.
Negative. So, what's the name for the negative ion? We talked about this. It's not being challenging. Alright, anion. What's the positive one?
Cation.
Cation. Okay, I was like, okay, I know we talked about physical science, but I'm pretty sure we had to have talked about it way back in chapter 2. Alright, so make a note for that. So the chemical bond determines the physical state of matter, the shape and properties of the matter. It also determines the type of forces that exist between the molecules themselves. What?
Forces?
Forces. So, do you know what force is? I don't think we talked about this in chemistry, talking about physical science.
A very large being that has large legs and he said horse.
Force.
Oh, not horse.
Force.
Can I answer?
What is a force? Alright.
The amount of power it takes to move an object.
Good job. So it's a push or a pull. And so it's the
Whoa!
idea of pushing or pulling an object forward.
I didn't
So
take this one.
if Ethan goes up and shoves Chris, don't do it. But if you did, that's
would
the
not move
idea
'cause
of
he's
a
stiff.
force. What?
I would not move because he's a
Oh,
It
really?
depends on how
Do you
much
want to
force.
test that?
We're not testing it.
Do you want to test
No,
that?
it'll be bad. Alright, so your book points out that ionic compounds and molecular compounds, they have very different properties. Your book gives you the chart at the top of the page. You don't have to know the chart right now because we're going to talk about it later on. But your book points out that there are several properties of ionic compounds. These are crystalline solids with high melting points and boiling points. They conduct electricity well. They're soluble in water. And their aqueous solutions also conduct electricity well, but typically they are insoluble in a non-polar solvent. So your book doesn't tell you the reasons why, but does anyone think they know why is it soluble in something like water, but it's not dissolvable or insoluble in something that is non-polar? Anyone think they know?
What does non-polar mean?
Yeah, I know. Your book hasn't told you yet. We talk about physical science, so I know you at least learned it 2 years ago, but that was 2 years ago for some of you. So does anyone know what's the difference between like water and oil?
Oh, oil.
I think I got it.
Yeah, like the density.
Partially, yes, but oil is
I know oil
non-polar.
separates from water.
Yeah, and water is polar. So that's how come you have one substance dissolves in polar, but it won't dissolve in a non-polar or an oil substance. Does anyone remember what's the general rule that says polar dissolves in polar and non-polar dissolves in non-polar? It's been a while.
Don't get chased by a polar bear.
No. Alright, so it's light, and the general idea is light dissolves light, or it has to be the same. We'll talk about the reasons why, so if this is not jogging your memory at all, it's okay, we'll talk through that. So, molecular compounds, these have low melting points, they do not conduct electricity, many of them are insoluble in water, their solutions do not conduct electricity well, we'll talk about the reasons why, and most of them are soluble in a non-polar solvent. So again, just telling you, here's the chart. You don't have to understand it right now though. Alright, so bonding and the octet rule. Finally, your book decides to tell you about the octet rule. So I can finally start quizzing you over it.
Oh,
So,
what?
yeah, the octet rule, your book has not officially asked or told you about it, so that's how come I haven't asked any quizzes about it or quiz questions about it. Finally, I can make a note for it. The most important factor affecting how atoms form are chemical bonds with the number of valence electrons in each atom. Remember, what is a valence electron, Ethan?
Yeah, I forgot.
The outermost electrons.
It's the outermost electrons. Like, for example, fluorine has how many outermost electrons, Chris?
9.
That's what I put. 7.
See, I
You
don't
put
know.
9?
Okay, why'd you put no, thinking it through, why, so, the 9 in fluorine, you're right that there is a 9 in fluorine. What does the 9 refer to?
Oh.
Okay.
It's the atomic number.
It's the atomic number, and the atomic number is the what?
The mass.
Nope. Alright, what does the 9 refer to, Ethan, since you're asking? It's the atomic number, but what makes up the atomic number? Breathe, Ethan. Alright, what's it refer to?
Protons. Right?
The what?
The amount of protons.
Yeah, I thought you said fruiton. I was like, I have no idea what a fruiton is. But yeah, so just make a note, the atomic number refers to the number of protons, so don't let that confuse you. So look at the valence, so look at the group. So group 17 has 7 valence electrons. Group number 2 has how many, Ethan?
2.
2. And then group 13 has how many, Quentin?
9.
What?
9.
Ethan, it's not your turn. What?
3.
3. Okay, so y'all get it. Alright,
Oh,
so your book points out that atoms tend to react chemically to achieve a noble gas electron configuration. Noble gases have how many, Chris?
According to my test, 18.
It is 18. Okay, so 18 is the group. How many valence electrons do they have? 8. So they want to have the same number as the noble gases, so 8 valence electrons. We call this the octet rule. So make a note of that. It's finally at the top of page 130. So make a note for it. So your book points out, typically you can look at the main group elements, look at the ones, that's a good way to tell for it. Alright, so anyone have any questions about this before we start talking about ionic bonding? Alright, this is the first type of chemical bonding, is the ionic one. This one has to do with the idea of transferring electrons. I'm going to make that slightly larger for Jamie, because I feel like that's a little bit too small. Let me make it a little bit larger. Yep. I didn't look at the size, and I feel like it's too small. There. Now I feel better. Save. Alright, so ionic bond, transferring electrons. So this is whenever you're having one electron being given away to somebody else. We've already loosely talked about this already, even though your book decides, oh, I guess I should talk about it now. So that's part of the reason why I go a little bit longer in the other chapters, because it makes more sense as we go through it. So which seven says the metals, non-metals, or semi-metals typically want to throw their electrons away? Alright, Quentin.
What is it?
Between metals, non-metals, semi-metals.
Metals.
Why?
Because they have fewer valence.
Yeah, they typically only have 1 or 2. So again, group 13, they start to get a little iffy. But groups 1 and 2, they only have those outermost electrons of 1 valence electron or 2 valence electrons. So which is easier, lose 2 or gain 6? Ethan.
Gain 2. Lose 6. Lose 2.
Lose 2, okay. So that's the reason why, my metals go, okay, I'd rather my next shell is already pretty much full. So I'm going to throw off my outermost 2, and I am now happy and satisfied. So that's how when we say it's transferring electrons, I'm going to throw mine away. What is it, Ethan?
Still wonder what that feels like.
Transferring electrons, referring to filling full.
Feeling happy.
Happy and satisfied.
So transferring electrons. So they form an ion. Now remember, what's an ion, Chris?
Electron. Proton.
What? Okay, it has a charge. So if it's gained electrons, will it be positive or negative? Good job. So what do we call it? It's a negative ion.
Anion.
Good job. What if it's lost electrons? What do we call it? Good job.
You know,
Alright.
someone carved something into the desk of a friend.
Yeah, someone already told me that this, I think that one was previously.
M
though, the-
plus E.
Yeah.
Do not say anything that was not me.
Alright, so, just making out forms ions, it's the charges though that are holding it together. That's what holds my molecules together. It tends to be metals and non-metals. Why is it typically the type of bond between a metal and a non-metal, thinking it through? Alright, Chris?
Because it comes semi-metal.
No. Alright, Clinton? Alright, why is it the ionic bond that holds typically a metal and a non-metal together? Like, for
Opposite
example, we're gonna
charges.
talk about, yeah, that is it, I can tell, like sodium
Yes.
chloride, because sodium shows up with how many valence electrons? Ethan?
Let me guess. 7, 8, 1.
1. So, it wants to lose its 1. So
Nine.
No,
chlorine,
it's 9.
What?
It's 9.
for sodium?
Yes, oh,
Alright, chlorine shows up with how many valence electrons, Chris? 7. So how many more does it need to be happy? 1. So sodium throws its electrons to chlorine. Chlorine's now negative 1. Sodium is now positive 1. So those charges is what holds it together. So your book has the diagram trying to show you how it looks or how it looks. I have a moving diagram to help show. This one's a little bit dramatic. Again, as a side note. Guys, it wants to load. Hurry. Or not. Alright, so for this one is sodium, this one is chlorine over here. So that's how come they have one little electron out here. Now you'll notice it has how many electrons on the inner layer? Ethan. How many electrons are in the circle?
8.
8. So if it loses its 1, what does this outermost circle become?
7.
Okay, sorry. If it loses this electron, what does this circle become?
What do you mean does it, what does it
Okay,
become?
so which one's the outermost layer right now? This circle or this circle?
Oh, okay, so that one becomes out.
Yeah, so since it's 8 there, will it be happy and satisfied? What?
Yes.
Yes, it will be. So, this video is a little bit dramatic in how they show it. So if you watch the left hand, you notice, there it goes over and it hops over. So again, watching it because they drew it really quick. So, you notice here's the electron. There it goes. So, both of them are happy now. So, counting up chlorine. Chlorine has 8 now in its outermost shell. This one also has 8. So, both of them are happy and satisfied. But it's the charges that pull them together. So, that's the idea of ionic bonding. Anyone have any questions about ionic bonding?
Not really.
Alright, so again, we're going slow because I want you to understand it really well. Make a note of these 3 ideas or properties for it. With the idea of it's the transferring of electrons, let me go back, that it forms the ions, and the ions is what holds them up together, and it tends to be a metal and a non-metal. So make a note of all that. So your book's just talking about the example with sodium chloride. So they color coded it to me to help you see it a little bit easier. You don't have to know the colors because that's not real or accurate. But it's just fun, but okay. There's an example. Alright, you have a question, Chris? Just making sure, because Jamie can hear you better than I can. So, just making a note over this, but you'll notice that, okay, these form up these ionic crystals of the idea of the, as a charge over and over and over again. So, we use the smallest ratio one. Have we talked about, what do we call, I think it was way back in chapter 2, chapter 3, with the idea of what type of formula is it if it's the smallest ratio? Starts with an E. Alright, I'm telling you now that, so this is the empirical formula, or it's the smallest one, it's that simplest ratio. Because it's the idea, since this is positive, if I have a bunch of chlorines, I'll have other chlorine, that's not an L, I'll have other chlorines be attracted to it as well. Kind of how like if you have a positive magnet, and it'll attract a bunch of other, it'll attract a bunch of negative magnets, right? It's not just the idea of just one magnet goes to it typically. It's the idea you're going to have a bunch of negative around it. So if it's negative, what will also be attracted to it, Quentin? Positive. So you're going to have the others form up around it as well. So you can get this repeating pattern over and over and over again and build up a giant crystal from it. So that's what this picture is showing you, that this is just the smallest ratio, or the simplest ratio for it, or the simplest pattern. We call it the empirical formula or the formula unit. It's 2 terms for the same thing. Alright, anyone have any questions about that? Does anyone know what sodium chloride is? You probably eat this on a daily
Table
basis.
salt.
Yep, table salt. This is
I don't
regular
hate
table
it.
salt.
Just kidding. I
Hey.
have to search my food that.
I figured.
I have
Alright.
heart problems, I don't eat sodium.
I say, you should try not to. Typically Americans, we get enough sodium already as it is, so for the why you want to eat as less as possible. Alright, anybody have questions about this?
So what is pepper? Like, one more
What?
question. Pepper, what is that?
PE.
Okay, it's not an element, so it's a compound.
No elements are in it?
What?
What elements are in it?
Oh, I don't know off the top of my head, I'm sorry. It's not simple like this.
Radon.
It's probably,
Uranium?
oh, not,
Yes.
no.
Yeah, we're gonna die.
Brown used to create the time machine.
That's why we don't want the 900 anymore because we're eating,
Gotta move on. Alright, so your book gives you off another one for it, that sometimes you can have different substances, as long as it's those charges holding them together, that's what makes your ionic crystals stick together. Your book gives you the example of magnesium and oxygen. Alright, so magnesium wants to lose how many electrons? Because remember, you can't have electrons just being thrown away into infinity, they have to be going somewhere. So the charges have to match up. Our magnesium wants to lose 2. How many does oxygen want? Quentin? 2. So that's why this one looks like this. So magnesium throws both of its electrons onto oxygen, and oxygen says, yes, thank you, please, and it takes them both. So sometimes you don't have it to where it perfectly matches up like that, and so you need to start having practice figuring it out. So looking at it like this, potassium has how many valence electrons, Ethan? Hard for Ethan.
6.
Potassium?
Okay?
Potassium, yeah.
That's on my left or right side?
It's on the far left.
Quentin, shut your mouth.
I don't
5.
like to listen to questions.
One.
1. Alright, so once it throw off its 1. Oxygen still needs how many though?
6.
Okay, so starting with 6. So how many does it need to be happy?
2.
It needs 2 more to be happy. So if
What?
it, so if it takes potassium's 1, is it happy and satisfied? It only needs 1. Alright, so what can I do to balance this out? Because oxygen is still unhappy.
Balancing equations again.
What?
2.
Add 2 what? 2 oxygens or 2 potassiums?
2 oxygen. 2 potassium.
2 potassium. So the idea of potassium number 1 goes,
9.
here's 1. Potassium number 2 says, here's 1. And now oxygen says, I am now happy. I have both of mine at the same time. Alright, anyone have any questions about that? Because you're going to have to start having practice to like have practice with the
These
molecules.
are balancing equations again.
What?
This is balancing equations.
Yeah, basically. Now keep in mind, you're going to have to come back to this.
It's like a gerbil.
It's literally what it was making me think of as well. Alright, stop playing with your water bottle. If you need to drink it, then drink it. Just stop playing with it. Alright, so this is going to come back though with oxidation reduction reactions or electrochemistry in a future chapter. That's why your book's making you practice with it right now. Alright, your book points out, another example, it can form between groups of ions as well. Like for example, anyone remember what this is from your ion chart way back on page 44, alright?
Ammonium.
Ammonium, so this one has a positive 1 charge, and it can form up to this as well for it. So you can have ammonium chloride. Now keep in mind, ammonium, if it has this positive 1 charge, what does that mean?
It's poisonous.
It's in the group 1. Or the 1, it's the 1 electron thing.
Yeah, it's chunked off 1 electron. So chlorine wants to take how many?
1.
1. So are they both happy and satisfied?
Yes.
Yeah, so you can form up ammonium chloride like this. What is it, Chris? You have a question?
I said 1.
Okay. So your book gives up a last one for it with magnesium and another one. So magnesium and then SO4. Do you remember what this one is?
Sulfate.
Sulfate. Good job. So sulfate, do you remember how many it wants to take? It's been a while, I know.
It wants to take
2.
2. Magnesium wants to lose how many?
2.
2. So these 2 are able to balance out as well. Alright, anyone have any questions about that? Magnesium sulfate, as a side note, is known as Epsom salts. Do you gentlemen know what you use Epsom salts for?
Bath salts?
Okay, what do you use it for? Yeah, so
Bathtub.
with basketball, your legs might have been feeling really sore. Probably not as much anymore. Probably those first couple of days, it was agony because your legs were not used to it anymore. That's the reason maybe why you use Epsom salts for a little bit. Alright.
I did.
Bath salts work better.
What?
Bath salts work better. Same thing.
Yeah, it's pretty much the same thing. Now sometimes they have like different floral scents added to them, or to make it smell extra fruity or extra floral.
You don't want to smell extra fruity.
If you want, okay, yeah, not extra fruity, but it's the idea. If you want, if that's what you want to do, it's your house. Alright, so ionic compounds, if you don't know, they do not consist of molecules, so they form up these crystals. I think that's pretty much everything. Alright, anyone have any questions about this? Nope. Okay, let's go over the example on page 131. So, tell which of the following compounds would be expected to contain an ionic bond, and of those compounds containing an ionic bond, which would you expect to have the most ionic character? Which one would be the strongest ionic bond, based on how far away they are from each other on the periodic table? Alright, so the first one, it gives you, I'm going to have to erase part of this, that way Jamie can see it. Alright, the first one it says is Na-O2. Alright, so would that be an ionic bond?
Yes.
Yes.
Why?
Because God said so.
Why? There's a reason why that you're going to put on the test.
Because they are ionic compounds.
Because oxygen wants two and Na gives off one, so you
Yeah,
need two
they're
and
all
Na gives
compounds.
two.
Alright, so
Sure.
is this between a metal and a non-metal then?
Yes.
Yes, okay, that's the basic answer. But yes, it is because the metals want to give them away. Alright, so magnesium and chloride, dichloride. Alright, so is this one ionic or not?
Yes.
Why?
No.
Metal and non-metal. Alright, phosphorus and trichloride, metal, non-metal. Is it a metal and a non-metal, and is it ionic? No. This one is actually covalent because phosphorus is a non-metal, so it's a non-metal to a non-metal. So they don't want to, phosphorus does not want to give its electrons away. We'll talk about what type of bond this is, maybe today, maybe, depending how fast it goes. Maybe tomorrow. Alright, so looking down at the next one, so RBI. Alright, rubidium iodide. So, is this one a non-metal to a metal?
Yes.
It isn't?
Yeah. No.
So, what's iodine?
Iodine is a non.
Iodine?
Iodine is a semi-metal.
It's a non-metal. It's a non-metal to a non-metal.
So,
It's a
rubidium.
semi to a. Where's rubidium?
Alright, the semis are the orangey ones in this diagram.
Yeah.
It's on good one.
Alright, so is iodine a semi-metal or non-metal?
It's a halogen.
Alright, so is the halogen a non-metal, semi-metal, or non-metal?
Non-metal.
What? Non-metal. It's a non-metal. Alright, rubidium, RB, I gotta find an RB. Here it is.
So it's a metal to a non-metal.
Yeah, metal to non-metal. So is that, would that one have an ionic bond?
Yes.
Yeah. Okay, so for this one, we have an ionic bond. Okay, I'll try to put it up here. Ba chlorine. Alright, so would this one be an example of an ionic bond?
Yes.
Why?
No.
What? Non-metal to metal. Alright, so which of these would have the strongest metallic character saying, the strongest ionic character, which one's the farthest apart on the periodic table?
RBI.
Well, okay, so how many do you think this one?
RBI. Wrong.
Alright, how many do you think this one? I'm gonna go ahead and write this in, because no one wants to talk about that one. Alright, how about this one? Alright, how about this one?
Yeah.
Alright, Chris, which one are you picking? This? This? Alright, looking at the periodic table, sorry Danny. Alright, so you have barium and chlorine, and then you have rubidium and iodine. So which ones are farther apart?
Rubidium ion.
You sure?
Yeah, be sure.
Alright, because they're on the same row and they're just straight across. Wow.
Farthest apart.
Wow, barium and chlorine, I have whole energy levels in between them. And they're really far apart. It's rubidium and fluorine. Alright, anyone have any other questions about that one?
Rubidium and fluorine.
I'm sorry.
I got it right.
Barium and fluorine. Alright, anyone have any questions about that one?
Nope.
Alright, so the next type of bonding, covalent bonding. I can talk about it for 10 minutes. Alright, so covalent bonding. This one is between non-metals and non-metals. I'm going to make this bigger as well so that Jamie can see it.
28.
28.
Alright, so
That's large.
we'll make it a larger form.
35.
Alright, these are sharing of electrons because it's in both of their electron clouds. And it's the attraction to the electron cloud. The attraction to the electron cloud, that's what's causing them to stick together.
Attraction.
Attracto.
Alright, so it's the attraction of the electron that holds the atoms together. It tends to be between non-metals, so between a non-metal and a non-metal, since non-metals typically have how many valence electrons, Ethan?
7.
Alright, so yeah, the halogens have 7. How many does group 16 have? Chris?
9.
6.
Alright, do you remember what the special name is for group 16?
Chalcogen.
Good job. So group 16 has 6. Group 15 has how many?
5.
5. Group 14 has? Ethan?
4.
4, and then there we start hitting semi-metals again. Now, why do the non-metals want to stick with carbon? That starts off with 4. Which is easier? Lose 4 or gain 4?
Gain 4.
Carbon decides it's easier to gain 4, but
Get
that's
wrecked.
how come carbon is the first of the non-metals, while these turn into semi-metals and then metals down here, because since these get so large, they say, it's so far out there, and I'll just lose them. Well, carbon says, no, I have 4 right here. I just need 4 more, then I'm happy and I'm satisfied. So that's the reason why they shift over. While carbon's a non-metal, these are semi-metals, because they decide, I don't know, yeah, I can take them, I can lose them, it's fine. Either way works.
Question.
Wow, the ones down here, they're so far away at that point that they say, it's too much work, I don't want to hang on to them, you guys can just have them. Okay.
Why does hydrogen have its own color?
Alright, hydrogen has its own color that has how many valence electrons?
1.
1, so we stick it in group 1 by itself, but it acts like a non-metal, because hydrogen has a tendency to share instead of lose it. Hydrogen can lose it, but it's rare. Hydrogen tends to go, I only have 1 valence electron, I'd
It's a
rather keep
non-metal.
it, and I'd rather have another one with it. Hydrogen, since it has the same electron configuration when it gains 2 as helium, helium is so small, it's satisfied with only 2 valence electrons. That's kind of the exception to the octet rule, but that's because helium is so small. So once hydrogen gets 2 as well, hydrogen also says, okay, I'm happy. I don't have to have 8, I'm fine. But hydrogen and helium are kind of the exceptions to that. Everybody else says, nah, I'd rather lose it. Alright, anyone have any questions about that? That was good thinking though. So that table colors it gray to make it stand out. Wow, your book colors it the same bluish color as all the other non-metals. Alright, so this
Really?
is what?
Really?
Yeah, look at your, look at your favorite table in the back.
He's being stupid.
I don't have one in the back.
And you ripped it out. But that's part of the reason why if you look at it, then you notice, hey, it's the same color as all the other ones. And that's the reason why, because they're telling you, hey, it acts like a non-metal. Alright, so this is covalent bonding for it. So your book gives you the first example. It says, okay, for sodium chloride, sodium with hydrogen, that it can take it. For example, sodium has how many? Did I talk about this? Quentin? 1. So sodium 1, 2, gain 7 or lose 1? Lose. So sodium can say, I don't want it. I really, really, really don't want it. Hydrogen, you can take it. Take it! And it can force it onto it. Hydrogen goes, okay, I'll take it. And it pretty much just takes it, but it's not super happy with it. It doesn't typically do it that way. So hydrogen can take sodium's electron. It doesn't really do it that way. So because your book points out that, okay, it can. It's just not super common in how it happens. It's much more common for hydrogen to share. Next page. Alright, so your book points out that hydrogen typically forms up for the single bond. Now keep in mind, can you have just a single hydrogen atom floating around in the air? Or what does hydrogen typically do whenever it's up in the air? Anyone remember what's the common state of the
Turns into water.
No, because you have hydrogen gas in the air, but it's not just individual hydrogen atoms just floating around. How is it typically bonded?
2.
Yeah, typically 2 of them. Hydrogen is one of the diatomic elements. Well, there's typically 2 of them floating around in the air right now. So as you breathe, you're breathing in 1 molecule of dihydrogen. Now, hydrogen likes to have a buddy. This is the reason why. Because hydrogen starts up with how many electrons?
Must be nice.
What?
So it must be nice.
I know. Hydrogen starts up with how many electrons?
1.
Alright, other hydrogen starts up with how many electrons?
1.
1. They both start off with 1. So they decide, hey, you want to share? Okay, so each one brings an electron. Your book tells you as well that it color codes them, so that way both of us, also so that you can see it. In real life, you don't have different colored hydrogens and you don't have different colored electrons. Your book's just color coding them so that way you can see how they're being shared. So don't think of it as like, oh, there's different versions of an electron. No, they're all the same. Alright, so because of that, you're having one electron, you're having one hydrogen saying, okay, I'll share my electron with you, while another hydrogen says, okay, I'll share my electron with you. So both of us have two at the same time. Alright, so that is covalent bonding. That's whenever you're having the sharing, and since both of them are attracted to the electrons, because electrons are what charge, Ethan?
Negative.
Negative. So since they're both negative, the positive protons are both attracted to them at the same time. Your book gives you an example of carbon with 4 hydrogens bonded around it. So carbon, we'll let carbon be yellow. So carbon started with how many electrons, Quentin? 4. I'm going to draw one on each side just so that way I can go ahead and spread them out. Hydrogen each brings how many electrons? 1. So I have hydrogen over here. I have another hydrogen over here. I have another hydrogen over here. I have another hydrogen over here. So this hydrogen's sharing its electron and sharing one of chlorine, one of carbons. This hydrogen's doing the same thing. This hydrogen's doing the same thing. This hydrogen's doing the same thing. So is each hydrogen happy and satisfied? Quentin?
Yes.
Alright, now chlorine has its 4 electrons plus it has the 4 hydrogen electrons that are being shared with it. So is the carbon happy? I just said chlorine by accident. Is the carbon happy? Yes, so that's the idea of both of them are happy at the same time. What?
Am I happy?
Sorry, Chris. Alright, your homework for tonight. We'll stop there. Finish reading over this. So read page 132 through page 132 through 134. We'll stop there. So 132 through 134. Alright, answer on page 136, the concept review 1 through 6. You'll be fine. 1 through 6, and then hang on, I'm going to give you application.
What?
You want to give us more?
Maybe. Come on, think about it. Let's see.
Are you done? Shoot the plus button.
Okay, you're going to do application number, you can do 1 and 2. So, do the concept reviews 1 through 6, and then the application 1 and 2.
On what page?
On page 136. It won't take you long. You're going to go through it and realize that it's easy. So, concept review 1 through 6, and then application 1 and 2.
That's what they said about life.
Yeah.
Alright, so, you go over it. What type of bond is between a non-metal and a non-metal? Quentin? Between a non-metal and a non